Hello there, welcome back to today's video. We're going to be looking at paper 2 bubble pen feedback today. Again, make sure that you fully bubble pen your work. Alright, let's get started. Underneath the water, we already calculated it, which is 225,000. So what is the total pressure? The total is how much in total? The total pressure. Let's go to add 1 times 10 to the power 5. Okay, alright, and we just need to show it is roughly about that much. It is show that it is this one. That's what we need to show. There's only one mark. That's it. So one mark to show addition. So that's what you need to show. You're showing that you're adding them together. Now that's blah blah. So we got pressure, volume. So therefore that's one. We need to use an equation there. So P1, P1, 2. Now the pressure at the surface. So surface we know the pressure at the surface. We know the volume of the surface. So therefore P1 is this much multiplied by 0. Equal to pressure at the depth. So we already worked this out, isn't it? So we already worked it out. It is pressure at the depth. We already worked this out. Pressure at the depth already. Now the pressure at the depth of this, so the total pressure, we need to find it out. We need to work out. So P2 is actually the total pressure here, because that's how much pressure is on the balloon at the depth of 25. So all that pressure is on the balloon at 25 meters, at the depth of 25 meters. So therefore that's the pressure on it, and we need to find V2. Okay, so now we need to be careful when we are going to rearrange. Let's go with the whole thing divided by this much. And V2 is going to be 0.1. Okay, so that is the answer. So the issue that we have is people forgot the equation, and we forgot to identify that the pressure at the depth of 25, the total pressure exerting on the balloon is this much. Okay, because that's why the question asks us to. That's why the question pretty much asks us to find the total pressure first. Okay. Now this one is about specific heat capacity and using water. Okay, let's go back. Let's go. Keep going and see what we have. Find the specific heat capacity of water. Good. Okay. Now what we're going to do is we are going to start using the equation first. So we know that energy is equal to mc delta theta. So we arrange this, we got C is equal to energy over m delta theta. So this is the equation for specific capacity. Now, what do we have? What do we need in this case? Alright, so first of all, what do we need? So let's take a look. So first of all, what do we need? So the question says, what did the question says? The question says, you may draw a diagram if you want. You may draw a diagram to help you answer. Describe, and to describe, so we don't need to explain any details. Describe, so we've got these things here. So we've got the heater, power supply, beaker, water, thermometer, stopwatch. Okay, so these things. Alright, good. Okay. Alright. Now the first thing we're going to do is I'm going to do the easy stuff first. So we're going to measure mass. Now how do we measure the mass? We measure mass of water. Okay. Measure mass of water. Alright. Now, how are we going to measure the mass of the water? So there are a few things you can do that. Okay. There are a few things that we can do. So using, let's say, automatic scale, automatic balance. Is it automatic balance or okay, so, sorry, it's not automatic. My bad. It is electronic. Electronic balance. Now, how does this work? How does it work? So we put the beaker on the electronic balance, okay, and then we click on 0. So this will eliminate the mass of the beaker, and then what we can do is we can pour water into beaker, okay, which is on the balance to get this one. So that is a method to do that. Okay, now what we can do is there's another method. Okay, so there's another method which we're going to do. Now the other method is pretty much, so what we do is we measure mass of beaker, and then what we do is we measure mass of beaker plus water, and then we find the difference. So the difference will be the mass of the water. Okay, so that's how we're going to find the mass of the water, because that's the problem here. We have water. Okay, so we need to find the mass of the water. That's the problem. Right, now once we find the mass of the water in the beaker, so once we've got the mass of the water, okay, so what we're going to do is we are going to measure the initial temperature of water. Now how are we going to measure this? With thermometer. Okay, good. Alright, so therefore I can add the little diagram there as well. So I've got my beaker with water in it and my thermometer in it. Okay, to measure the initial water temperature. Okay, good. And then I'm gonna add, what does it tell me to add? Okay, heating. Alright, so heating when it says heating with power output, heater. Okay, with heater. Okay, alright, so add heater into water. So we add the heater into the water, and what do we do? Okay, so what we do, add the water to the heater. Okay, and then and measure the temperature after some time. Okay, so some time, I'm gonna say maybe, let's say 50 minutes. Okay, with stopwatch. Good. Okay, so we stopwatch, and of course, so measure temperature. Okay, so after some times, after 50 minutes, so using stopwatch, and this one is using a thermometer, of course. Okay, all right. Okay, so find the rise in temperature. Okay, so we can find the rise in temperature, or the increase in temperature. I think that's the one. Okay, so find the increased in temperature. Okay, because now we have the temperature after 50 minutes, and then we have the temperature initially, so we can do that. So what we can do is, so how can we do that? So final temp minus starting temperature. So this will give us delta theta. Okay, good. Okay, now we have delta theta, and then we have the mass. So this will give us the mass. So we've got delta theta, we've got the mass. Now we need to find energy. Okay, so calculate energy with E is equal to power times time. Okay, okay, power is equal to 50 watts. Okay, now how do we know that? Because it's given to us here. So power output is a heater. So power 50 watts of heater. Okay, so this is, sorry, heater. Alright, good. And then what we can do is we can use equation. Use equation to find specific capacity in this case. Okay, now of course we can plot a graph and so on and so forth, so you can go, how many marks is this? So 5 marks. You can go extra, you can say, record. So here we go, so you can say record the time intervals. For example, you can say, okay, intervals of times for every, let's say, 2 minutes, 6 minutes, and so on and so forth. Okay, then we get a series of data, and then we can plot a graph and so on and so forth. Yeah, so we'll also add it here. We can also plot, let's say, temperature versus time graph if we want. Okay, okay, and use gradient to find C. Okay, so this is what we can do. Alright, so let's move on. Okay, so what we have here. Alright, now calculate the energy. So this is specific capacity. We need to know the equation. I just put everything in the equation. The mass we know 75. Specific capacity we know 4200. And the change in temperature is what? So what is the change of temperature? The change of temperature is 65 minus 16. And we get 15, 123, 123 joules. Okay, 3 marks there. Good, in the pocket. So let's move to the next one. Now this is the moment question. So what is the equation for moment? Moment is equal to force times, look, perpendicular distance. So perpendicular distance. So we need to make sure that distance that we're writing down is perpendicular. So that's the questions they tell us. Good. Okay. Now we need to be careful if we're using the symbol. So m times f times perpendicular distance. Good. Now calculate moment. So by taking moment at support A, so support A, so A is a pivot now, so A is a pivot. So calculate the force F. Where's the force F? So this is F in this case. Okay. We know that the weight is this much. Okay, so what we have is we have a diagram. So we've got the pivot, we've got the force here, which is 260. We know how far it is. So this is how much is this? So this is 25. Okay, and then let me just change color pen. So we have this one, which we don't know, F, and we know that F is, how far is F? F is, so 55. So it's 55 plus 25. Oops. So 55 plus 25 away. Okay, good. Now moments are equals together. So what we need to do is we need to work out the moments. So the moments, so we got moments, we got, so we have anti-clockwise moment equal to clockwise moments. So anti-clockwise, in this case, which one is anti-clockwise? So which one is going to be anti-clockwise? So which one is turning anti-clock? So this is clockwise, okay, and the other one is anti-clockwise. So which one is turning this way? Let's take a look. So anti-clockwise is going to be like this. Clockwise is going to be like this. So which one of these forces are clockwise? So which one's anti-clockwise? So which one's turning the other way? So therefore is F. So F times 80 is equal to, which one's clockwise? So it's 260 times 25. Okay, and therefore we have F is equal to 260 times 25 divided by 80. Okay, and this will give us force of 81. Good. Let's move to the next one. Wait, have we done this? Why have we done this? Let's move to the next one. Okay, now what's this one? Now, if it is a rectangle, it is a resistor, but it is a rectangle with a arrow to it. So it is a variable resistor. Now, the variable resistor, what does it do? It varies. It changes. So what changes? What is the thing that changes? Okay. Now, why is it included? Now, a variable resistor is a resistor that changes, but why do we use it? So the question is, why do we use it? Okay, so it is it's a variable resistor. It's a resistor that changes value, but the reason we use it is, remember, so V is equal to IR. If current, so this is the current in the circuit goes now. If we are changing R, it means that voltage is changing. So therefore, we use it because it allows the voltage to be varied. It allows the voltage to be varied. That's why, because by changing the resistance, we can change the voltage, how much energy goes through. Good. Okay, so that's the one. Okay, so current and voltage. Okay, so we can see that as voltage is increasing, current increases until current becomes sort of like even, so it doesn't increase anymore. Okay, let's take a look. Equations. Okay, here we go. Look, the equations are already in the right order. So it's charge equal to current time. Good. Now determine the current in the lamp when the thing. Okay, so here we need to use a graph. So when the voltage is 10, the current is, so let's go to the graph. Voltage is 10, so it's 10. So 10 is here. So we go across, and then we go across here. So here we go. So how much is this? So 4. So 5 somewhere there. So this is 4. So it's 4, 8. So this is 0.48. Good. Now next one, we need to use the equation this time. So the equation to calculate the charge. So that's the equation. So charge equal to current time. time. So current, now we will know when the lamp is 10 volts, so that we know already that the current is 0.48 times 30 seconds. Okay, and this will give us 14, and the unit for charge is coulombs, capital C, coulombs. Good. Now calculate the time. We know the energy, we know the voltage. Okay, so calculate the time in this case. So which equation should we use? Okay, so energy that links time and voltage. So there's one equation. Voltage. Oops. So voltage is equal to energy over charge. Okay, good. All right, good. Now energy we know, and the charge we know as well. Oh, so we're looking for time, isn't it? We're looking for time. My bad. We're looking for time. Okay, we're looking for time, and we know the energy in this case. So the voltage we know is 10. The time, okay, so it's no longer 30 seconds anymore. So it's 9. The time is this time. This is the time. Okay, so we're looking for energy. So I'll rearrange these equations. Energy is equal to voltage times charge. Now, voltage we know is V multiplied by charge. Now, charge, we know charge. Charge is current multiplied by time. So if I go back, so here we go. Just charge is Q is equal to current multiplied by time. So I know this. So therefore, the charge. So I'm looking for okay. So I'm looking for time. I'm looking for time. So therefore, it's going to be energy divided by voltage and current. So this will equal to, so 25 0 divided by 10 times the current we know is 0.48, and this will give me 52 seconds there. Okay, so here we need to remember this equation in this case. Good. Now complete the, so here the student disconnect and then reverses it. What's going to happen? Okay, now if we have a circuit, what is the circuit? So here's the circuit. We have here the circuit. Now, so current right now is flowing in this direction. Okay. Now, if we switch connection, if we switch, so what? Which one are we switching? Disconnect. What are we disconnecting? Disconnect the cell. Okay, so changes the cell. So now look at that. Look. So we've got positive, negative. So the current. Let's say for the sake of this simplicity, the current goes from this side to this side now. Okay. Now, if we change this, so we've changed. If we change the cell, now the cell is like this. So therefore, the current will be going the other way. Okay, so we'll be getting negative current. We'll be getting negative current. So that's why on your graph, you're going to have the graph that goes down this time. So again, it should be the same. It should be roughly the same. So 12. Okay, so 12 is here. So 10. So when it's 10, we should be getting roughly at this point. Okay, so it's going to be. Okay, so let's have a look at 5. It goes down. So 5 is going to be here. Here we go. So nice smooth one like this. Here we go. Okay. It goes down to here because that's where it is here. Okay, so like this. So it should be like this, like an S. Okay, easy stuff. Easy stuff. Nice. How many marks is this? 2 marks. Nice. Nice and easy. Right, now let's take a look what we got. Now, instead of having the cell, we have an AC power supply. Now, what's going to happen here? We have a diode, and then it flashes on and off, on and off, on and off. Now, first of all, we need to see what happened. Now, AC. What is AC? I think it tells us already. Alternating current. Now, alternating current means it is current that changes direction. Okay, so the current will be going this way. Okay, and then after some seconds, it's going to go the other way. Okay, That's the first one we start with. Now, the second one we don't need to talk about is the LED. Now, the LED is light emitting diode. It is a diode. Now, a diode only allows current in one direction. Okay, so it means that if current is going the other way, then it will not light up. So that's why it's off. Okay, so so the LED only lights on if the current flows in one direction. If the current flows in the other direction, it doesn't light up. And the AC changes direction continuously. So if the current is going, let's say, in the purple direction, the diode will light on because the diode only allows current in in the purple direction. Now, if the current reverses because of the AC, let's say the current now goes the other way, so the red arrow. If the current goes in the red arrow, but the LED will stop it. Okay, so LED not light up when current reverses. Okay, good. And here we go to the multiple choice question. Nice and easy multiple choice question. Alright, let's take a look what we've got here so far. Okay. Okay, now we're talking about density. Now density we know. So let's take a look. Density is mass or volume. So I need to see so it's full. Okay, so show workings. Here, so show workings. Okay. Now we need to work out the mass of the liquid. So we've got the mass of the empty flask. We've got the mass, the total mass in this case. So the mass of the liquid would be the total mass 50, take away 34 divided by the volume of the liquid in this case. Okay. And this will give us 0.8, so therefore the answer is A in this case. Again, I need to see you working out. Good. Now, this one is Hooke's law, so we got unstretched. So that's the original one. The object stretch, the length is this. So we need to work out the weight. So weight is the force, F. So we know F equal to KE. E is the extension. Okay. And then the force F is there. Alright, so we can work out extension here. So we don't need the equation actually. So we just need extension and force. Okay, so here we go. So extension is equal to the final length, take away the initial length, which is 2.2. So therefore 2.2 is where? So 1, 2, so 2.2 is there. So we go across, then we go down, and we have 3. So the answer is D. Okay, so I need to see that these lines on the graph. Good. Now next one is which situation involves no work being done and no energy being transferred. Okay, so in this case, what is happening? So there's no work being done at all, and there's nothing. Okay, now let's take a look. A car skidding on the road. Now, car skidding. So if skidding on the road, skidding to a stop on the road. Now, for you to skid, you need to apply the brakes. So if you apply the brakes, that's friction. So friction. Okay, so energy being transferred there. So therefore, this is not the answer. Now, crane lifting up a load. So that is GPE. So it's going up. So therefore, that's not the case. Now, the heavy load hanging from a strong bar. So if you have a strong bar and something is just hanging up. Now, it is not moving, it's just hanging up. So energy is not being transferred. You're just standing there. Okay, so it could be this one. Now let's take a look. Student dragging. So it's dragging, so that's kinetic energy. So energy being transferred. So it's going to be this one. So therefore the answer is C, because C, there's no energy being transferred. It's just hanging up there. Good. Now, there are several ways of which energy can be transferred to a small block. So stable. So here we go. This block there on the table. Now, how can we So which one's correct? Which one is correct? Okay, now we heat it up. Yeah, so energy is transferred to it. We shine light on it, so sending wave to it. That's correct. Put current through it. So put current through it, so it gets shocks. So it also heat up. So therefore, it is D. Okay. So all transfer energy to block. Okay, so write this down. Let's go to the next one. Okay, now this one is which is the case. So which man does the most work on the box, and which one gained the most energy? Most energy. Okay, let's take a look. Now this guy is pushing the block, but the block is not moving because the block is already there. Okay. Now this one is lifting up, so the box needs to go all the way here, all the way here. So therefore, so here is pushing it, but it can't push it because there's no space to move, so there's no movement. Okay, so here it's lifting it up, so it moves. So okay, so work done equal to, so work done equal to force times distance. Okay, so moved in same direction of force. So which one has moved in the same directions? Therefore, it's Q. So therefore, it's going to be Y. So this is the answer. The answer is D. Okay, now this one, mass is this. Surface is this. Okay, find pressure. Pressure is force over area. Now the force is what? So now the mass, so it needs to be converted. Okay, to what? So the mass must be converted to kg. It's going to be 0.4. So the force is the weight, so mg over area. So mg, so 0.4 times 10 over the area. Now the area is going to be this times this, so therefore it's going to be what? So 0.4 times 10 divided by 0.1, 2, and this will give us an answer of 200. That's the answer there. Good. Air is trapped in a bottle. So let's take a look. Air is trapped in a bottle. Now temperature goes up. Which one happens? So if temperature goes up, means that the particles start to move faster. So move faster. So if they move faster, then the kinetic energy goes up. If they move faster, there's more energy. So more force, therefore more pressure. Okay, so there's more pressure. So which one is increasing? So therefore that's the one. Again, so I need to see that you've written this part down. Good. Now convection is what? So convection is only in fluid. So fluid is gas and liquid. So which one is gas and liquid? Here we go. Good. Here we go. Now students rub the plastic rod cloth with a cloth. Okay, so here's a cloth. So with the rod, that's the rod. Okay, now the rod becomes positive. So it means that it's losing electrons. So what happened? I already told you there. It's losing electrons for it to become charged. If it becomes positive charge, it means it is losing electrons. So therefore it's C. Good. Now this one is what? Calculate the current, blah blah blah. Okay, so this one's straightforward. So V is equal to IR. So V is 6. I is this much. Okay. So we're looking for now the resistance is the total resistance. So 3 times 3 at 5. So equal to 8. So 6 over 8 is equal to I. I is equal to 0.5. So the answer is here. Good. Now, which one describe what happened? So here, so this is X. So X is a thermistor. Now, thermistor is if temp goes up, then the resistance, goes down. Okay, so it is inverse proportional. Good. Now, there's two options. There's A or D. Okay. Now, if resistance goes down, so we know that V equal to IR. So if R goes down, V goes down. Okay. So V goes down across X. Okay. Across X. Now, this here is a series circuit. So series voltage equal to shared. All right. So if V across X goes down, then V across Y goes up. Okay, so therefore the answer is going to be B. Good. Again, so I need you to see this explanation in your book. Sorry, not in your book, in your paper. Now this one here, what we have, a current is connected to the main power supply. This is this. A table decorated has 3 of these lamps connected in parallel. Okay, what is the rating fuse going to be? Okay, so now for this one, what do we need? So what do we need? So we got a lamp is connected. So we got okay. So one lamp take this much current. So therefore, if they are in parallel, okay. So lamp, that's not the correct drawing for lamp. So lamp is like this. So one lamp, 2 lamp, 3 lamp. Okay. All right. Let's go. Now one of them is 0.6. The other one is 0.6. The other one is 0.6. So how much is it in total? So therefore, total current is 0.36 times 3 because there's 3 of them. Okay. 1.8 amps. Okay. Now we want the fuse to be able to take this much current. Okay. Now if the fuse is below this, then the fuse is going to blow and the circuit will stop. So which one is suitable? So it can't be this one, can't be this one, can't be this one. Therefore, it has to be D in this case, okay? Because D is the only one able to support this one. All right, and also we know that in parallel current splits, the current is parallel splits. That's why one is 0.6, second one 0.6, 0.6. For the total one, the total current is 3 times that. And therefore we need to pick one which works. And okay, this is it. This is it then. All right, again, so make sure, especially for the multiple choice, you have the full working out there. Okay, and just check again if you're not sure. Do let me know what's going on. Do let me know.